Hi and welcome. So at adjoe, we've been running almost exclusively on Spot instances for well over 6 years now. For the vast majority of this time, we've been using Spot Ocean as our solution for cluster autoscaling. But as we grew, in terms of both traffic numbers as well as number of instances, we encountered more and more problems with it, and we became less and less fond of relying on a third-party service for one of the most critical parts of our infrastructure. Because if a traffic spike hits you and you cannot scale your cluster because a third party happens to be unavailable at the time, well, tough luck. That, in addition to the ever-increasing cut that we had to pay to Spot Ocean, led us to explore other alternatives. And what we found is Karpenter. By now, we've been running Karpenter in production across multiple Kubernetes clusters for more than a year. And today I want to share with you the problems that we've encountered during this time, as well as all the lessons that we've learned along the way. But first, a few words about myself. So I'm Marius. I work as a DevOps engineer at adjoe, a fast-growing adtech scale-up based in Hamburg, Germany, where I mostly work on increasing the reliability and cost efficiency of our systems. I was an open source contributor. I worked in CoreDNS in the past. I made some smaller contributions to Karpenter by now, and also maintained some Nix packages, but that's enough about me. When it comes to adjoe, I gave a talk previously on an SRE day in London in Q1 of this year. That was in the end of March. Since then, our headcount has grown by over 50%. We now have more than 300 EC2 instances running our backend. Sometimes it's more, sometimes it's less. The reason for, I will talk all about today. And with this infrastructure, we are now handling more than 5 billion API requests every single day. First, I want to give you this very high-level overview of our current backend, and I don't want to go into the detail of all of this, but what I want you to take away from this is that by now we're actually running quite a lot of open source and self-hosted solutions. So you can see here Trino, Kafka, Druid, OpenObserve. We are running all of these on our own infrastructure. But things haven't always been this way for us. When we started out, we used to rely quite a lot on proprietary solutions and AWS managed services. Only over time, as we grew as a company, we found us to be able to do more things ourselves and also wanting to become more independent. Today, I want you to focus on the compute part of this diagram and to take you on the journey where we went from Spot Ocean, which is a proprietary solution by Flexera for cluster autoscaling, to Karpenter, which has been more recently developed by AWS. You can also use it across all the other cloud providers, by the way. And let's first talk about the problem we're actually trying to solve here. So when you're operating at a certain scale, you'll find that your numbers of traffic vary vastly throughout the day and throughout the week. At some parts of the day, we might be getting 3 million requests. At others, we might be getting 7 million. And to handle this, we need very different amounts of infrastructure. And without autoscaling, we really only have two options available here. We can either provision our infrastructure for peak load at all times, which would mean that we would be overpaying for the vast majority of the time. Or we can provision ourselves for the average, but then we would not be able to handle the peak, and therefore our customers wouldn't be happy with us. We don't want to do either of these things, and therefore what we need is autoscaling. When it comes to autoscaling specifically in the context of Kubernetes, you can do three things. You can scale pods vertically, which means you give them more CPU, more RAM, more resources in general. You can scale pods horizontally. That means you create more replicas running the same workload, and then you distribute the traffic between them. And once you have done either one of these things enough, you will find that you're running out of capacity in your cluster. And then the cluster itself has to scale, which it does by adding more nodes to it. And this last part, this is what we call cluster autoscaling, and this is what I want to focus on today. How it works in a little bit more detail. When you have pending pods in your cluster, the first thing that will happen is that the scheduler comes in and tries to place them on any of your existing capacity. That is, the nodes that are already running in your cluster at this moment. Now, once it cannot do this anymore, the pods will be deemed unschedulable and the autoscaler will kick in. In this case, Karpenter, and will communicate with your cloud provider, be it AWS, GCP, Azure, and will provide a new nodes for you to run these pods on. But it won't stop here. We then go a step further and we look at our current state of the cluster and we try to optimize it further. You can see here that at first we had these 3 small nodes to run our workloads, but then Karpenter found we could do the whole thing cheaper by running on a big node and 1 small node instead. And so we consolidated towards that. In a nutshell, we are just always monitoring for pending pods, provisioning new nodes as we need them, and trying to optimize the state of our cluster to run all of our workloads as cost efficient as possible. There's currently 3 main solutions when it comes to cluster autoscaling. There's Cluster Autoscaler. This is part of the Kubernetes project itself. There's SpotOcean, which is a proprietary solution developed by Flexera. And there's more recently Karpenter, again developed by AWS. And when we started out, Karpenter wasn't a thing yet. And since we wanted to rely so heavily on Spot instances, SpotOcean had very neat features at the time that made it an easy choice over Cluster Autoscaler back then. But as things have matured, we decided to give a closer look to SpotOcean in comparison to Karpenter. And first of all, if you look at both of these solutions from an architectural point of view, with SpotOcean, you have the Spot instance controller running as part of your cluster. This is what will always monitor the state of your cluster and report it to SpotOcean. So as soon as you have any pending pods, the Spot instance controller will first report to the SpotOcean server, the part that is handled by Flexera. And they will, on your behalf, provision new nodes in AWS as you need them. On the other hand, if we do the same thing with Karpenter, this third party completely disappeared from the picture. Karpenter talks directly to AWS and provisions any new nodes as we need them. This comes with both upsides and downsides. With SpotOcean, we got really nice observability and resource recommendations out of the box. It was really easy to see what was going on in our cluster. With Karpenter, we have to do more things ourselves. We only get metrics, we have to build our own dashboards. For resource recommendations, we now use other solutions, such as Goldilocks. But what we gained is more trust in our own infrastructure. We don't rely on this third-party service anymore. And Karpenter is fully open source, so whenever there's any issue going on, we can really dig into and see what's happening in our cluster and find out what's the root cause. Further, we don't have to pay any cut to SpotOcean anymore. And last but not least, we also found Karpenter to be faster when it comes to node provisioning. So when you're running with like more than 300 instances, you will find that a node joining and leaving your cluster is something that happens almost every minute. And at this point, this operation being super fast matters a lot for our reliability. And for all these reasons, we've been very happy with Karpenter for over a year now. But let's talk about the actual migration process, about how we went from one cluster autoscaler to another in production without causing any downtime in the process. So when we install Karpenter on our cluster, for this we use the Terraform AWS the sub-module they have for Karpenter, as well as the official Helm chart. But now Karpenter is installed in our cluster, and it's not yet really doing anything. Because there are no pending pods, there's no reason for Karpenter to do anything. What we do now is we reduce the maximum number of SpotOcean that you can configure by 1. And once we do this, there should be pods going pending because SpotOcean doesn't have the capability to provide enough nodes anymore. And these pending pods, they will then slowly get picked up by Karpenter, who starts provisioning new nodes themselves. And we do this whole process one by one by one, slowly making sure that all the new nodes come up on the side of Karpenter first before we disrupt any further. And with this whole process, we've been able to do the migration without causing any issues. And from here, we lived happily ever after, is what I would really like to say. But of course, that's not what happened. There were a couple of issues that we found after our migration process. The most significant of which is that we suddenly found broken nodes showing up in our cluster. This means there would be nodes who are in an unreachable state. From the point of view of the cluster, these nodes were unreachable, no pods would schedule on them, but from the point of view of the cloud provider, this is still a healthy node and it would never go away. So these nodes would just sit there indefinitely until we manually terminate them. And this could happen at any time. This could happen at 4 AM and cause a bunch of alerts to go off. So this was really a big issue for us, and as we investigated further, we found that both Spot Ocean and Cluster Autoscaler would handle these cases for you automatically. There's also a variety of reasons why this can happen. You can, for example, be unlucky and just get a bad hardware instance from the cloud provider, or your kubelet could for whatever reason. And in these cases, Spot Ocean and Cluster Autoscaler, they would after some time just terminate this node for you, so you could move on with your production cluster. But Karpenter, at least until version 1.1, did not. So we had to find another solution. We couldn't just wait for version 1.1, because when we adopted Karpenter, it was around May 2024, and version 0.37 just came out. So there was an open issue for this whole thing, but there was no solution in sight yet. So what we did is to create our own custom controller for this. It's quite simple, honestly. We just watch for detained unreachable. Then we wait a certain amount of minutes. We found 10 minutes to work really well for this. And then we go and terminate the node. We also open sourced the whole thing. And sure, by now, Karpenter also does this. If you are running on more than version 1.1, Karpenter will also terminate these nodes for you. But to this day, they are still not allowing you to configure the timeout. So you will always have to wait for more than 30 minutes for these nodes to go away. But with our own solution, we found it to work quite well to terminate nodes after 10 minutes already. And we are still running it to this day. With this, I want to talk about all the lessons that we only learned in a year of running Karpenter in production. And the first one comes down to a decision that you have to make very early on when you adopt Karpenter. So Karpenter, being the thing that managed all the nodes in your cluster, also needs a node to run on itself. And to solve this, you really only have two options. You can go with either Fargate or a managed node group. Fargate being the AWS serverless options, where you can run a pod but not really think about nodes at all, or a managed node group being a group of nodes that you have to manage yourself, and Karpenter isn't aware of them at all. Back in these days, we decided to go with Fargate because it seemed to promise to us the greatest reliability. Since Karpenter is really a critical piece of our infrastructure, we wanted to be on the safe side. And we thought Fargate would be exactly that. There were a couple of issues, though, that we encountered over time. Two of them quite early, which is when you adopt Fargate in your cluster for the first time, the communication with regular nodes actually won't work. So you first have to make some security group modifications that your Fargate pods can even communicate with regular nodes in your cluster. And then you have the whole topic of daemon sets. Since like a Fargate node is not really a node, but it still shows up as a node from the viewpoint of your cluster and from the viewpoint of your daemon sets, they will still try to schedule on these Fargate nodes, and they cannot. So for the second part, for the daemon sets part, we found a solution in giving all our daemon sets the following node affinity to say when it's of compute type Fargate, hey, then don't even bother, don't try to schedule on this. We added this node affinity to all of our daemon sets, and we found that some open source Helm charts also provide this by default by now. We even went out of our way to also add it to the Prometheus node exporter Helm charts. So if you decide to go on the same journey, we maybe made your life a little bit easier, but to be honest, I would not recommend to go with Fargate at all. I would recommend to use a managed node group, because over the time, we encountered more issues. So, as I said before briefly, we are using the Karpenter submodule of the Terraform AWS modules. And they recently decided to drop support for service accounts in favor of pod identity. But now we run into the problem that, well, pod identity isn't supported by Fargate yet. And I'm not sure if it will be ever. So at this point, what we had to do to be able to upgrade is that we implement all the support for service accounts now in our Warper module ourselves. And it's just all these little edge cases that you run into where you have Fargate running in your cluster, which is just too different from a normal node to be handled the same case, and you always keep running into edge cases. And if I could go back in time and have to make the same decision again, I would just go with a managed node group to have more unified approach of how I can handle all the things in my cluster. And let's talk about disruptions. So when we first adopted Karpenter, we saw quite a lot of them. In Karpenter, there's really 5 reasons that are known for disruptions. There's spot interruptions, These ones you can't really do much about. It's when you run Spot instances on AWS, AWS can basically take them away at any moment with this 2-minute notice. That's the deal you're making. Then there's underutilized, which says that Karpenter found a cheaper way to run the workloads in your cluster, and so it disrupted your nodes to go towards that. Empty means that Karpenter found an empty node in your cluster, so a node with only daemon sets on it. Drifted means that the configuration of the node configuration changed. Maybe you wanted to use a new AMI, and now Karpenter is disrupting your nodes to move towards this new configuration. Last but not least, insufficient capacity. It's not really a reason for disruption, but it's saying that AWS couldn't provide the type of node that you asked for. For us, this usually means that we go from Spot to on-demand. And because when we are going on-demand, we also want to go back to Spot as soon as there's capacity available again. So it also causes this flickering between Spot and on-demand, and it causes more disruptions indirectly. Now, when we look at one of our node pools early on when we adopted Karpenter, we see that we have quite a lot of disruptions here. We have a lot of insufficient capacity, we have a lot of empty, we have also some underutilized, and of course the usual Spot interruptions. And what you can see is at some point we made some changes that caused things to be way more stable. The first thing we did is to introduce a lot more instance types into the node pool so that Karpenter has more ability to find the correct Spot instance for us. If we go and we look at the node pool name, you can see here it's called Kafka Network Optimized. The reason for this was that we only included the network optimized instance types, which at the time was only 6. And of course, if you only include 6 instance types in your node pool, you will quite often run into the case where AWS just goes, I cannot give you a Spot instance for this request right now, and then you have to go back to on-demand. So what we did was to first change some architecture of our backend that we didn't need the network optimized nodes anymore. And then we could actually include a lot more instance types into this node pool. We also included larger instance types, as the 2x large and 4x large, because Karpenter will generally look at the resource requests and will make the best decision for you in terms of cost efficiency anyway. And with this, we never saw any insufficient capacity for this node pool from there on. The next change we made was to increase consolidate after. This is about these empty kills you saw here. So what we saw happening is that Karpenter would provision a new node for us, and then it would immediately terminate it again. Because the workload would take too long to actually schedule on this node, and Karpenter is very aggressive that when it sees an empty node with only daemon sets, it immediately goes and disrupts it. By default, consolidate after is set to 0 seconds, and we found to just set it to 3 minutes would help us to get rid of all these empty kills, to let Karpenter wait a bit before it actually disrupts these nodes. And last but not least, there's of course disruption budgets. I assume most people in SRE are already familiar with the normal pod disruption budgets. So you have a deployment with 3 replicas, you might be fine with one of them being disrupted, but not 2. You can encode this in a pod disruption budget, and Karpenter will generally honor these things. But there's also a Karpenter disruption budget, which is a more global disruption budget. To showcase a little bit the things you can do with this, you could, for example, say, hey, I want you to disrupt all of the nodes. You can disrupt as many nodes at a time as you want. Just go nuts. But only do it on a Sunday, and then for 24 hours. So on the whole Sunday, we say you can do as many disruptions, as many cost optimizations as you want. But for the rest of the week, we define that no nodes can be disrupted at all. We start this from the Monday, and we go for the rest of the week. It's not a configuration we're actually using, just to explain a little bit the capabilities that you have with these disruption budgets and the things you can do. What we're actually doing, though, is to just have a default of always allowing only 5% disruption for the reason of underutilized and drifted. For empty nodes, we're generally fine to let Karpenter disrupt as much as it wants to. This is generally safe, and since 5% are always being rounded upwards, so Karpenter should still always be able to at least disrupt one node at a time for underutilized and drifted. This, so far, has been working great for us and has given us more stability in our cluster. And with all these reasons, we came to the graph as you've seen it before. That was the wrong direction. The graph is, you've seen it before, that really we reduce disruptions quite a lot. And there's also a new proposal that I want to give some attention to that wants to introduce a savings threshold into Karpenter, where currently, as soon as Karpenter finds even a 1% cost saving in your cluster, it will try to consolidate towards that. What this proposal is doing, it wants to introduce the setting where you can say, hey, only if this new node you're giving me is actually 10%, 20%, or even 50% cheaper, then I want you to disrupt. Otherwise, don't bother, just keep the cluster as it is. Which I find really quite a useful setting to make the whole state of your cluster a little bit more stable again. And I would love to see this in Karpenter rather sooner than later. So check it out, maybe give it a thumbs up. I would like to see this. And when it comes to conclusions, what we've learned in the year of Karpenter is that it's really important that you, first of all, have your resource requests set right, so you know how much these workloads actually need, so Karpenter can look at these things and make the right decision what nodes to give you workloads. You want to have your disruption budgets in place so that Karpenter never goes and disrupts any of your critical workloads in a way that they cannot sustain. You want to have as many instance types as possible so that Karpenter can always find a spot instance for you. This has really helped us a lot. In the beginning, we were trying to optimize too much to give a node pool only the exact correct instance type. But as we give it more choices, we found that Karpenter really optimizes towards the right choice anyway. And I would also advise to use as few node pools as possible. Just start with one, call it default, and only if you find that you really need to, then create other node pools. And as I've mentioned, if I could go back in time, one thing I would really like to do is to use a managed node group instead of Fargate, as the experience of using it and the difference it creates in how you have to handle all the nodes in your cluster so far really hasn't been worth it. And last but not least, what we saw since we've adapted Karpenter is 5 to 10% faster node provisioning compared to Spot Ocean. And again, this really matters at a grand scale, where you have nodes coming and going from your cluster all the time. This helps a lot with the stability. We see reduced cluster cost mainly from not paying the cut to Spot Ocean anymore. So when you have to give around 20% of your spot savings to this third party, and you then have 300 nodes, all spot, and most of them 2x large, you can do the math yourself. Also, I find the developer experience overall better, as with Karpenter, your node pools, your node groups, everything is just custom resources as we natively know them in Kubernetes, or with Spot Oceans. These things don't really exist from the viewpoint of the cluster. They're just settings that you set on Spot Ocean itself. So with all this, I want to point you to our engineering blog, a few talks from my colleagues, and also the pull requests that I've mentioned throughout this talk. And with this, I'm still here for questions. I'm still around for a while. If you have anything you want to talk to me, feel free.
Are there any burning questions right now?
Yeah, thank you, Marius, for the talk. So I would like to ask is how does Karpenter actually manage multi-cloud or multi-cluster setup, if it's like natively supported within the app, right?
Come again? I didn't quite understand it.
How does it manage multi-cloud setup or multi-cluster setups?
We are running one instance of Karpenter per cluster. So we haven't really had to think much about how it would act when you try to manage multiple clusters from one instance. So that's how we've been doing, to just have one Karpenter per cluster. And that's been working well for us so far.
Mm-hmm. So it doesn't like handle cases where like running a node in a different cloud provider would be actually cheaper?
We've not been trying to use it across multiple cloud providers. I'm not sure if it would actually work. If you could have like a GCP node joining the EKS cluster, I'm not sure. Mm-hmm. Personally, I don't think so. But yeah.
Thank you.
You mentioned about Karpenter's disruption budget.
Mm-hmm.
it doesn't apply to Spot instances, right? Because my understanding is that those can be claimed anytime, but yeah, maybe.
Yeah, of course. The Karpenter disruption budget is for the disruptions that Karpenter can actually influence. So underutilized, empty, drifted, all these kind of things you can manage with the Karpenter disruption budget. But spot interruptions, of course, AWS doesn't really care about your disruption budget, and it will still only leave you the 2 minutes to interact, and you will still have spot interruptions, yes.
In the controller you develop and you have in your GitHub repo, it is for lingering nodes that when that happens, do you have in that repo, documentation about the whys, because it will be interesting for me to check it.
This was for the cases where we specifically saw these nodes that were stuck in unreachable. And so what we saw is that we had to interact manually to terminate these nodes. So what we did was simply to just wait a certain amount of minutes. If the nodes get stuck in this state, then we would just terminate them through the API of the cloud provider. And that would generally lead Karpenter to give us a new node, and things would go into a fine state. Of course, this doesn't let you troubleshoot the actual problem. This is the argument that Karpenter originally had for not developing this feature earlier. So they wanted to let you time to investigate the issue, but we found that we just wanted to move on as fast as possible.